I want to thank Hugh Geller, who's here today. This was Hugh's idea. In fact, Hugh would first offer to help organize this. And we thought that, you know, Hugh being a grad student on the market himself, we wanted to make sure he had a fair chance to also speak. But we should all thank him for having such a nice idea. Champ was his, so that I already forgot what champ means, Sean.
It's right there on this commutative and homological algebra market presentations.
Exactly. So thank you, Hugh.
Yeah.
And go ahead, Sean.
Okay, so thank you everybody for coming, and especially Eloisa has been doing the lion's share, whatever that means. She's been doing all the work on getting this together, so let's thank Eloisa for all the work that she's been doing organizing this. And I get to do this sort of ribbon cutting ceremony of doing just the fun part, which is to introduce the speaker. So it pleases me immensely to introduce our first champ speaker, Keller VandeBogert. Keller, oh yeah, perfect. Earned his, Keller, your master's degree is from Georgia Southern, right?
Correct.
Yeah, and is now currently a PhD student at the University of South Carolina, working with Andy Kustin, the other USC, and as this seminar title indicates, is on the market this year. So, and didn't memorize Keller's title, but I'm sure that he will remind us of some approximation of that when he says.
Oh yeah, about
Keller,
that. Yeah.
The floor is yours.
Well, first of all, of course, thank you for the invitation, and I should thank Hugh then as well for even having the idea. This is a great idea, and I'm very thankful to have been invited. So today I want to talk about what I've called Tate-like complexes and applications to DG structures. My handwriting will get better as I do the talk. It always starts out really bad for some reason. So yeah, I typically when one starts to talk, they start with kind of a motivating problem. And in my case, the motivating problem is going to be really annoying to state without introducing a whole bunch of machinery first. So bear with me while I first give some definitions, and then we'll start working on some examples and we'll get into what I really want to deal with. So of course, the first thing I should talk about is the definition of a DG algebra. And in particular, I care about DG algebra structures on complexes, chain complexes. And so first thing is let F. So F is the complex and the differential is D, so be a complex. F has the structure or admits the structure of an associative DG algebra. There's an I there, okay, yeah. Of an associative DG algebra. If there's a product, so a graded product, so we go from Fi tensor Fj to Fi plus j. And moreover, I should say, I'm assuming it's associative. So if there's an associative product, going here, and moreover, such that we have the following kind of standard, I guess one would call it the Leibniz rule identity. So that if I do di plus j of a product of terms fi times fj, so I'm going to write the product like that, then this is equal to di times fi, di of fi times fj plus -1 to the I fi times dj of fj, where I'm assuming that fi lives in capital F of I. So, all right. So that's the first thing. Moreover, I want to talk a little bit more about what it means for this DG algebra to exhibit something called Poincare duality. And first, before I say that, I should say I'm also assuming all of my DG algebras are commutative. which means the following. So also fi times fj is graded commutative. So this is -1 to the I times j of fj times fi, where we have the same convention for the f's. All right. Moreover, f exhibits Poincare duality if, first of all, I'm going to write f sub m needs to be isomorphic to just the ring R. Of course, I didn't start by saying this. R is a commutative Noetherian ring. This is just a running assumption. I forgot to say it, but yeah. So f sub m is isomorphic to R, where m is the length of the complex. And I have the following pairing. So if this, the multiplication map going from fi tensor fm minus I to fm is perfect. And I'll say what perfect means. So perfect means that the induced maps, right? So kind of using the Hom tensor adjunction. So fi has an induced map to fm minus I dual, and likewise the other way around. And I'm assuming that these are isomorphisms. If these induced maps are isomorphisms, that's what it means to be a perfect pairing. So yeah, anything else I want to say about that? No, I think that's all. So yeah, I gave kind of this relatively long definition right off the start. So hopefully I didn't lose like half the audience immediately. But let's do an example. And really this is like the best example you could have in mind. I think it's an example that's fairly well known. Maybe you don't think about this example in this way, but you can. So let's say the canonical example of a Dg algebra exhibiting Poincare duality is the Cazul complex. So this is kind of defined in, I'll define it using coordinates even though I hate to, but I will. And so in this case, we have that f is, I'm going to write it as a free module on some basis elements, f1 up to fn. And then I'm going to take an arbitrary map, psi, which goes from f to r. Then the Cazul complex is essentially just the exterior algebra. And this is not always the first way it's introduced, but in my opinion, this is the most elegant way. So K sub I is defined to be the ith exterior power of F. And we have a differential, which I'll write D, which goes from wedge I minus one, or sorry, wedge IF to wedge I minus 1F. And this takes an exterior product. So what indices should I use here? So J1 up to Ji, and this gets mapped to, we'll do the sum, -1, L plus 1, yeah. Psi of F, J, L. So of course, okay. And I'm running out of room slightly. So J1 wedge dot dot dot. J sub I. All right, where the hat on the element means exclude this one from the exterior power. All right, so I'll zoom out a little bit so it's a little bit more seeable in its entirety. So this is the Cazul complex. It's a complex. One can check it if they feel like it. I'm not going to prove that, but it's true. And moreover, there's a natural candidate for a product on it, right? This is already defined as an exterior algebra. And notice I use the word algebra. So we already have a multiplication, right? So the multiplication is going to be the map wedge I, wedge J, F, and I can just wedge these two things together and get a thing in the I plus J exterior power. So the nice thing about this one is that it's associative kind of for free just by the way the exterior algebra is defined. And it turns out associativity is pretty rare for DG algebras. To be honest, it almost never happens. It only happens for short complexes or really well-behaved complexes, which is kind of surprising. That's typically the axiom everyone forgets when they're proving things, but in this case, it turns out to be the most important one. So here's our multiplication. I'm not gonna prove it. Someone can check as an exercise. Satisfies the Leibniz rule, or whatever you want to call it. So satisfies the product rule. And moreover, this product, this is kind of a standard result, I believe, but this product is a perfect pairing. So that's where the Poincare duality comes from. And this is kind of to be expected, right? We already know that the Cazul complex is self-dual. And if you're a Poincare duality algebra, that has to be true just by what I had written above. You get isomorphisms between the complementary degrees. So it satisfies the product rule and also exhibits Poincare duality. So the Cazul complex is a great example to have in mind for the two definitions I just introduced. All right. So next thing I want to talk about is I want to give a theorem. And I had the idea that maybe I could just introduce Tate-like complexes just right off the bat with no motivation. And I realized that was a terrible idea, so I'm not going to do that. But I'm going to introduce it instead as by the following theorem, which is a pretty well-known theorem. So theorem. So this is due to Buchsbaum and Eisenbud. And of course, I didn't look up the date for this, but I'm pretty sure it's 1977. Someone can check me on that, I guess. So we have the following theorem. So let R mod I be a ring with projective dimension 3. Then the minimal free resolution of this quotient is going to admit the structure of an associative DG algebra. And when I write DGA, I mean DG algebra, okay. So I want to give at least an outline of the proof because the proof is, I don't know, the first time you see the proof, you think, huh, what a great idea. And after you look at it a little longer, you, when you see other papers on DG algebras, you see something similar appear. And this is one of the first examples it was used in commutative algebra, it seems. And so I want to do at least introduce it, and this is going to lead naturally into Tate-like complexes in more generality. So the proof is, so let F and D denote the minimal free resolution of R mod I. So B MFR, minimal free resolution. Do I have a question? Oh, 1977 is correct. Good, cool. So let's take our minimal free resolution and then we consider the following complex. So consider we have, I'm going to denote it D sub 2 of F. This is not standard notation, but I do it this way. And so we have F1 tensor F2 to F2 direct sum, second exterior power of F1, F1, and then to R. And so our differentials I'm going to denote like this, not 3, 2, del 1, where they're defined as follows. So basically you define them to formally satisfy the product rule, all right? So we have D3 of F1 tensor F2 is going to be set equal to, I do D1 of F1 times F2, right? D1 of F1 is a scalar, so multiplication is well defined there. and then minus, so I'm forcing it to satisfy kind of the graded Leibniz rule. So F1 wedge D2 of F2. D2 of, so D2 restricted to the direct sum and F2 is just the original differential. So that one's no problem to define. D2 on the exterior power, same idea. So F1 wedge F1 prime. Those are two elements in F1. So this is equal to D1 F1 F1 prime minus D1 F1 prime F1. And then the last one, D1 is just equal to D1. Del 1 is equal to D1, or whatever that symbol is called, partial 1. I don't know. Okay. And so what do I do with this? Well, I can take a comparison map. It just exists no matter what. So choose any comparison. So I'll call it C for comparison, going from D2 of F to F that extends the identity map in homological degree 0, all right? In particular, what does this induce? So this induces, I'll call it psi 1, going from wedge 2 F1 to F2, right? Because in our complex D2, in homological degree 2, we had wedge 2 F1. So this comparison map is going to send this to F2. And I also have a map psi 2 going from F1 tensor F2 to F3. And these are the two maps I use to define my product on the complex. So use these to define the products, right? Since it's length 3, I only need to define the product between things of homological degree 1 and 1 and 1 and 2, because anything after that has to be 0. And so we use these to define the product. And moreover, since our comparison map is a morphism of complexes, if you just trace through what that means, this means that these maps psi 1 and psi 2 will for free satisfy the product rule, all right? And so that actually is no problem. The one thing that everyone forgets to check is associativity. And in this case, it is going to be associative. And it's for the following reason. So basically, this is a length 3 complex. So D3 is injective. And so if you want to show that the associativity terms cancel out, it suffices to show that D3 applied to them cancels out. And I'm not going to give the full details, but when you apply D3 to it, everything breaks up perfectly because it already satisfies the product rule and everything just cancels out. So since D3 of the associativity term is 0, the original associativity term must have been 0. So you have an associative product. So what I'll write is apply D3 to the difference. Psi 2 of psi 1, F1, wedge F1, tensor F1 double prime minus psi 2 applied to F1, psi 1, F1 prime, wedge F1 double prime. And when you do this, as I mentioned, everything's going to kind of split up perfectly and you'll get 0. And also, you only have to check, the only triple product that's non-trivial is between 3 things of degree 1, just because it's a length 3 complex. So this is the only thing you have to check. Right. So,
Keller, can you hear me?
Yes.
Oh, terrific. Juliet has a question.
Oh, sorry.
No, you're
That's
good.
all right.
How do you define the product on, I'm confused how you're defining the product on F1. So like, you have a map from wedge to F1, but how do you define the product of like A times A?
Yeah, so the product of, yeah, I should have said that. So A times A then, so take 2 things that are in this. So A times B is going to be defined to be the image of psi 1 A wedge B. So that's how you define the product for 2 things in homological degree 1. Does that make sense?
And if A equals B, it's just 0 Is
Yeah,
that what
yeah.
you're saying?
It'll be 0.
Okay, so that was my question, was whether
Oh,
zeroing out the squares.
of course, yeah, yeah. And that comes for free just because we induce it from the exterior power. So yeah. Any other questions? No? Okay. All right, so let's continue. So if you've seen this proof before, then you're probably not thinking anything of it. But if you haven't, you're probably wondering, what is this D2 complex, right? Like, this is weird and interesting and kind of just comes out of nowhere. And so it's often called the symmetric square complex. So D2 of F is often called the symmetric square. And it applies for complexes of arbitrary length. There's no reason that you can't define it for bigger length complexes. And depending on who writes about it, they'll either use divided powers or symmetric powers. I prefer divided powers. But kind of what I want to get across today is that this is a specific example of kind of a degree K Tate-like complex, right? And so now we're going to actually talk about Tate-like complexes. And so the setup is kind of as follows. So let F be a complex as before. And in my case, I only care about complexes where it's a cyclic module in homological degree 0 or just a free module of rank 1. So with F0 equal to R. Then I want to first introduce the following notation. So N sub A. Don't ask me why I picked the letter N. I just couldn't think of a letter. Okay, so N sub A of Fi is going to be defined in the following way. So if I is odd, then I want to take an exterior power. And if I is, or sorry, if I is even, then I want to look at the divided power. If you don't know what the divided powers are, I'm not going to define them fully here, but basically, it's basically the symmetric algebra, but with a different multiplication. The multiplication there is exactly the transpose of the co-multiplication on the symmetric power algebra. Like, they're formally dual to each other. I like divided powers because they work better in positive characteristic, basically. But that's not too important. Also, so notice, we always have a map, so I'll denote it by partial or del or whatever it is. That goes to Fi minus 1 tensor and A minus 1 of Fi. And the way to do this is, well, I can go down here. There's always, on either of these modules as above, there's a nice natural co-multiplication map. And so I'm going to do co-multiplication and split it up in the following way. So I can rewrite it as Fi tensored A n A minus 1 Fi. And then to go back up here, I can just do Di tensored the identity, and that'll put me exactly where I want to be. So Di tensor 1. All right. And now I want to give the actual definition for the Tate-like complex. All right.
Keller, would it be possible for you to say a few words about co-multiplication?
Yes. Do you want me to? No, I'm just kidding. So yeah, let's take a look then. So co-multiplication on the exterior algebra is kind of like the most natural way to split up things in a way that retains the asymmetry, the skew symmetry of taking exterior powers. And so as an example that I like, so the Cazul complex, the differentials in the Cazul complex can always be rewritten as a composition, actually this exact composition. But just as a small example, if you have so suppose you have 3 basis elements, F1, F2, and F3, then the image of co-multiplication, the 1, so image under the 1, 2 co-multiplication is going to be the following. So it sends it to F1 tensored F2 wedge F3, and then minus. So the reason we get a minus is because you look at the sign of the element inside of them once you take the exterior product again. So this will be F2 tensor F1 wedge F3 plus F3 tensor F1 wedge F2. And the reason you do this basically is because the term on the other side has all the same asymmetry properties. So if I can switch 1 and 2 on this and introduce a negative sign, and the same property holds for the image of this element. So basically, it's dual to multiplication is kind of the short answer for it, hence the name co-multiplication, I guess. But this is an explicit example of co-multiplication. Does that suffice as an answer? I'm unsure.
Thank you.
Okay. Any other questions? All right. So let's talk about the Tate-like complex. So a degree K Tate-like complex is the complex. So I use the notation D sub K, which I realize agrees with the divided power algebra. This is kind of intentional, but also a bad use of notation. But just remember that if I'm applying D sub K to a complex, I mean the Tate-like complex. And if I'm applying it to a module, I mean divided powers. So D sub K of F with the following definition. So in homological degree J, this is going to be defined to be the direct sum, and I want to sum over all tuples satisfying the following. So first, their length n, which is the length of the complex. Sorry, I didn't say that. I'm assuming the complex has length n. I want that the sum of these things is equal to k, and then I also want that the sum of I times a sub I is equal to j. And then what I'm going to do is take a tensor product of all the terms that appear in my complex without the term in degree 0, just because it's a cyclic module, it doesn't really contribute anything. So this is n a sub n fn. All right. And the differential, I'm not going to write explicitly. I'm just going to say it's induced by this del, this partial, whatever you call it, that I had written up here. It's going to be induced by this by using kind of the formal product rule. So del goes from dkf in degree j to dkf in degree j minus 1 is essentially, as I just said, the form induced by delta as above. Induced by del as above, induced by partial as above. I don't know. As above. Okay. So yeah. Where have these appeared before? So that's a good question. Hopefully this would be a terrible use of notation if D sub 2 didn't agree with the symmetric square complex, and it turns out that it does. So D sub 2 of F is exactly the symmetric square. And where have these appeared before? So they've appeared before in multiple other works on Dg algebras. No one ever really gives them a name besides for the symmetric square part. So Buchsbaum and Eisenbud obviously use them because I gave the theorem by them. Andy Kustin and Matt Miller use this extensively. This is how they kind of define the first try of their multiplication for resolutions of grade 4 Gorenstein ideals. The only problem with that is that it's not guaranteed to be associative, but then they modify this induced product until it becomes associative, basically. So for grade 4 Gorenstein ideals, minimal free resolutions of grade 4 Gorenstein ideals, I mean. Also, Andy Kustin used them again much more recently to build matrix factorizations, or maybe I should say matrix factorizations. And also, this is the only other place that I've seen this appear. So they've also been called Weyman-Lebelt complexes in the case where F0 is not cyclic. So if F0 is not cyclic, or I don't have to assume that it's a cyclic, basically. But these are called Weyman-Lebelt complexes. I'll just write this. And the only place I've seen this called this is in Vasconcelos's book, The Arithmetic of Rees Algebras. That's what he calls them. I don't know if that's the official name. So Weyman-Lebelt complexes. And these are used for resolving exterior powers and symmetric powers of modules. So yeah, they were introduced originally by Weyman in a paper. He had proved the existence of these things called the lower order Buchsbaum-Eisenbud multipliers, and his proof involved the use of these complexes. So yeah, this is where they've appeared before. And what did I want to say after this? Oh yeah, so let's get into the actual setup, the main setup of the talk. How much time do I have?
I'm sorry, before you go ahead, let me ask a question then. I guess I was sort of expecting, because you're calling them Tate-like complexes, I was expecting that maybe the Tate resolution would be a Tate-like complex.
So this is why I call them Tate-like. So the Tate complex is strikingly similar. It's almost the same thing, but the Tate-like complex is you do a similar idea, but what you do at each step is, if it's not exact at that step, if you have a cycle which is not a boundary, then you formally adjoin a boundary to make the complex acyclic. In this case, these complexes, I don't care about making them acyclic. So it's not an example of a Tate-like. It's not an example of a Tate-like complex. Yeah, but it's heavily inspired by Tate complexes, hence the name. So yeah, that's why
I guess there might be Tate complexes that are Tate-like complexes from what you just said.
Oh yeah. So in the case, if this is already acyclic, I guess this would be a Tate complex. So yeah, that's probably a good point. But in the case where the degree 0 part is R, it seems to be very rare that it'll be acyclic. So yeah, but yes, it can happen that they do agree.
Thanks.
Any other questions? So, okay. So let's introduce kind of the main setup for the rest of the talk. So what I care about in this case is going to be looking at, so I'm going to have the following setup. This one is going to be a length 3 complete intersection, maybe instead of length 3, grade 3. And you are going to be a grade 4 Gorenstein ideal. So yes, I intentionally said grade 3. Grade 4 Gorenstein ideal. And then what I want to do is I'm going to take M to R mod I is at Dg Algebra, an associative Dg Algebra minimum free resolution. Minimal free resolution. And also I can always guarantee that I can always choose this resolution to be such that it also exhibits Poincare duality. And also I'm going to take K to R mod A to just be the Cazul complex of length 3. All right. And so with this data, I'm going to just choose a comparison map. So alpha going from K to M, and I want to use this, I want to choose it so that it's extending the identity in homological degree 0. Okay. All right. Yeah. So given this data, I'm going to give the following result by Kustin and Miller. So I'll call it theorem. So this is Kustin, Miller. Oh, I actually wrote the date. All right, cool. So this was from 1983. And it's the following. So if you let everything be as above, I'm not going to define the following word. It's not important for the rest of the talk. But I want to let I prime be a tightly double linked. So I want it to be tightly double linked to I. Then there exists some element R in the ring R and a complex which I'm going to denote by F of alpha comma R. And this is called the big from small complex sometimes. So big from small complex, often also like Miles Reed has dubbed it Kustin Miller unprojection as well. So it goes by a few names, but I'm just going to call it the big from small complex. Such that F of alpha comma R is going to be a resolution of I prime, of R mod I prime. Okay. And so now I can finally say the first question of, or the main question that I'm trying to answer in the talk is this resolution always an associative Dg algebra? And kind of the spoiler is that the answer is yes. The answer was already known for a pretty long time, assuming that that 2 was a unit in your ring. So answer is yes, if 1/2 belongs to R. And so this was proved by Andy. So Andy Kustin in, I think 94. And it's based heavily, the technique of proof is based very heavily on a previous construction by one of his students called a complete higher order multiplication on this resolution M. So based heavily work by Palmer, right? And so she constructs these things called complete higher order multiplications, and the proof that those things exist, like division by 2 is used way too often for one to really get around it. Like it's just everywhere and it's very hard to get past it. And so maybe you're asking like, okay, I don't really care about Dg algebras, but why would this be interesting to me if I don't worry about them? And the answer is, well, I don't know. But what I think is this is a main step. So this is a main step in proving that the minimal free resolution of a grade 4 almost complete intersection also admits the structure of an associative Dg algebra. Like the existence of this Dg algebra structure is very essential to that. This is a main step. Is an associative Dg algebra. And so what I was interested in when I originally looked at this is I kind of wanted to remove this assumption that 1/2 belongs to R. And as I kind of already alluded to, this is very hard because what it basically does is it puts you back to square one, because Palmer's work uses it so often that you really just cannot get past this assumption. All right, and so the method of proof originally employed really uses these things called complete higher order multiplications. Method of proof uses complete higher order multiplications. And I'm not going to define these. The definition is a little bit messy, and it's not particularly enlightening either, but these things exist. So complete higher order multiplications on M. And so what I do is, well, I basically go back to the start, and instead of constructing these things from the ground up, I construct something slightly weaker, but is still just enough to get the job done, basically. So I'll just say, but good enough for what I want. And so kind of the short answer, so how am I on time? Okay. So what is the short answer here? So idea is I want to build maps. I'm going to call them X. X goes from wedge 2 M1 to M2. And this is not just the DG product. It's going to be something that's quite distinct. And also X transpose, I'll call it, going from M1 tensor M2 to M3. And the way I'm going to build them is they're going to be induced by homotopies arising from morphisms of Tate-like complexes. So induced. From morphisms of Tate-like complexes. And so I really just want to use the remainder of the talk just to give a very broad overview of the proof. The proof itself involves a lot of computations and a lot of identities, but I think it's useful to kind of look at the high points of the proof, or at least get an abstract view of it, instead of worrying about all the nitty-gritty details. And so more precisely, what I do is I construct a morphism in the following way. So I construct this C, I'm going to call it C bullet. And this is the first time, at least that I have seen, where a Tate-like complex of degree higher than 2 has been used for DG algebras, basically. So D3 of M, and I'm going to send it to my Kazul complex shifted by -2. And the main point here is that this is the Kazul complex. So in other words, it's acyclic since it's resolving a complete intersection. And so if you have a comparison map of complex with the end map being acyclic, then you're going to have, basically your comparison map has to be null homotopic by some homotopy that I'm going to call H. So this implies that C is null homotopic or homotopic to 0. And what I'm then going to do with this H is I have kind of the following picture. So I've got D3M in homological degree 4. H4 takes me to K3. And also K3 is just R, and this is isomorphic to M4, right? Just because M is a Poincare duality algebra of length 4, so the last module has to be isomorphic to R. So these are isomorphic. And living inside of this D3M in homological degree 4 is the following. And so what I do is I'm just going to follow this diagram along until I get to M4. So I want to look at this induced map, which I'm going to call capital Phi. So look at Phi. Which is defined as the composition of all the maps above. And now, so when I'm happy if I get to this point because I'm living in a Poincare duality algebra. So if I have any map that acts like this, I can implicitly define maps using this Poincare duality that already exists. So I can define X and X transpose implicitly in the following way. So I have that X of, so theta 1 wedge theta 1 prime. I'll write where the thetas live after I write the identity. So this is equal to, I'm defining this to be the image of the following under this induced map phi. And likewise, this is also going to be defined to be theta 1 prime times X transpose of theta 1 tensor theta 2. Okay, where theta 1 and theta 1 prime live in M1. So remember, M is the minimal free resolution of my grade 4 Gorenstein ideal. It doesn't have to be minimal. And theta 2 lives in M2. All right, so here's where I start to wave my hands, basically. So I'll state this as a theorem, but like this isn't really a very precise theorem statement. So this is due to myself. Basically, X and X transpose satisfy a whole bunch of convenient identities. And as a consequence, I can use X and X transpose to induce or to endow this F alpha R, this big from small construction, with the structure of an associative Dg algebra, also exhibiting Poincare duality. Lots of things to write. So DGA exhibiting Poincare duality. And so, yeah, that's pretty much the main result. When I initially started on this problem, the original goal was to actually just remove the 1/2 is in our hypothesis from the proof that the grade 4 almost complete intersection, that admits a DG algebra. That turns out to be hard. This is kind of the main thing that I've gotten out of this, but I do think that that result, that is still doable. I just think that there's more work involved. And I really do think that Tate-like complexes will play a pretty big role in this. And not only that, I've really never seen, as I mentioned before, I've never seen anything higher than a degree 2 Tate-like complex used for DG algebras. And so I'm interested to see like what other applications these things have. Other than that, it looks like I'm right on time, so I'll stop there.
All right, let's everybody thank Keller using the silent clap method. Lola here thanks you as well, especially you set the bar high for ending on time. Any questions for Keller?
I have a question.
Yeah.
So this is Daniel. How are you? Nice talk, by the way.
Thank you.
So one of the things that I've been interested in with the DG algebra structures in the say the Gorenstein codimension 3 case, going back to the Buchsbaum-Eisenbud, is the way in which that extra structure allows you to give a fairly explicit parameterization of Gorenstein codimension 3 ideals and by extension Gorenstein codimension 3 varieties and things like that. Yeah. But the DG structure is of course an extra structure, right? So I was wondering, in these codimension 4 cases, or even some of the other cases you've looked at, how unique is the DGA structure, right? Is it kind of, is there some reasonable amount of, is it easy to explain or no?
So No. So Andy Kustin, my advisor, I asked him a similar question a while ago, basically about, because his interest for a very long time, and still is, was a complete structure theorem for grade 4 Gorenstein ideals, kind of using similar techniques.
Yeah.
And so I asked him, like, what do these products tell us? Can we get similar identities? And his answer is basically no, he doesn't think it's going to work the same. He spent so much time on it and kind of hasn't gotten this great structure theorem that he's really looking for. So the answer is, although these things always exist for grade 4 Gorenstein ideals, it seems like they're not as powerful for giving a structure theory as one might think. However, using these things, there is a complete classification of the Tor algebra structure for grade 4 Gorenstein ideals. So you can't quite get all possible DG structures, but you can get all Tor algebra structures. So I don't know if that really answers your question, but yeah.
No, that's helpful. I mean, I had a similar impression as Andy, that it's somehow, but I was curious. I'd never quite heard it phrased that way. Anyways, thank you.
Yeah, the closest thing to like a real structure theorem, and it's definitely not explicit, is Miles Reed's paper, the Gorenstein codimension for the general structure theory. It's a really hard read though, and again, it's not really like a concrete structure theory. Yeah.
Keller, do you want to say anything about the uniqueness question that Daniel asked?
Say again.
There was a question in there about uniqueness of DG algebra structures.
So they're pretty much not often. They're pretty much never unique, just because since you can, I don't know. I can't say anything concrete on this. Like in terms of grade 4 Gorenstein ideals, I suspect that it's not unique just because of the method that in which they're induced is like a whole bunch of re-choosing of homotopies to satisfy certain identities. And I imagine that there's no way to choose these homotopies uniquely. So I have no idea though on the uniqueness question.
In general, they're parameterized. I mean, DG algebra structures are parameterized by a big affine variety, right?
Probably,
Or,
yes.
I mean, big. It's got lots of equations and lots of variables. Whether it ends up being big is another matter, but.
Yeah. So, yeah.
Other questions for Keller?
So what's next for these Tate-like complexes?
What a great question. I do have a small result. I mentioned how Palmer had constructed these things called complete higher order multiplications. And this was essentially the content of her thesis. And it's a really, really complicated construction. And I do have a proof using Tate-like complexes that these exist. It's a much shorter proof. The only problem is that I still have to assume that 2 is a unit. So it's not proving anything new, but it's a much slicker proof, in my opinion. So yeah. And that uses like a degree 5 Tate-like complex. So that's kind of interesting.
Other questions for Keller? Using the old 10-second rule. For some sufficiently large value of 10. All right. Well, let's thank Keller again. Very nice talk, Keller. Very nice.
Very nice talk. Thank you, Keller.